everybody, my name is Jai Tao, and today we're going to be going over a very interesting new discovery about the latest exomoon candidate discovered, Kepler-1780-bi, which is a great step forward in the field of exoplanets and exomoons in general. And today's discovery was made and published in a paper by Kipping, Bryson, Burke et al., whom I'll be referring today as just our authors for the rest of this presentation. So let's jump right into it. One of the biggest questions facing mankind today is, are we alone? Or are there other extraterrestrial life on planets orbiting beyond our solar system, around other stars? And to answer this question, astronomers in recent decades have dedicated themselves to studying planets orbiting other stars, known as exoplanets. Since 1995, the discovery of 51 Pegasi b by Mayer and Quelaz, which is the first exoplanet discovery, this field has just exploded and exponentially expanded as we've improved our detection techniques and found more and more exoplanets and learned more and more about them. One of the most effective techniques for exoplanet discovery is known as the transit technique, in which we can detect the dips in a star's brightness whenever a planet passes in front of it. As you can see in this visual down here. And this is one of the, as I mentioned, this is one of the most effective techniques for exoplanet discoveries, being responsible for a majority of the exoplanets we know of today. With missions such as NASA's Kepler Space Telescope discovering up to around 2,000 exoplanets alone. And an interesting caveat or bias within this transit technique actually is the discovery of hot Jupiters. Because the transit technique favors the discovery of planets that are orbiting close to their star, which are very big, because large planets cause more noticeable dips in brightness, and with a shorter orbital period, they cause transit events more often, which make them easier to detect. And so this results in discoveries of huge gas giants, which were found to be orbiting very close to their stars in Mercury-like or even closer orbits. And these are known as I mentioned, hot Jupiters, which is a very interesting trend within the transit technique. With all that said, the transit technique nowadays is now being used to further our understanding of exoplanets, by now being used to potentially find the first exomoons, moons orbiting other planets outside of our solar system. Now, there are no confirmed candidates yet, but as I mentioned, astronomers are working on it today, including the authors of today, who've conducted a one-of-a-kind, never-done-before survey on 70 cool giant exoplanets discovered by Kepler. And cool giant exoplanets just refers to essentially not hot Jupiters. They refer to huge gas giant planets, Jupiter-esque, that are orbiting further out in from their stars. And this is because based on our current understanding and just looking at our own solar system, we believe that it's most likely to find exomoon candidates around gas giants orbiting further out. So let's jump right into how our authors conducted today's survey. So first, looking at the methods, our authors need to narrow down a list of candidates from NASA's exoplanet archives. And to do this, they first basically narrowed down planets that fit within the parameters of Jupiter-sized planets, at least 1 AU away, with a limit of up to 2 Jupiter mass planets. And based on this, our authors got a list of 70 candidates. Based on 70 candidates. Now, to analyze these planets, we first needed to conduct an isochrone analysis on their stars, because we needed to know the stellar properties of the host stars in order to get any information on the exoplanets that are transiting them. And to do this, as I mentioned, the authors conducted an isochrone analysis, which was essentially an observational HR diagram, which you can see over here, which graphs luminosity with respect to surface temperature and gives you a range of different stars, types based on this. So what an isochrone analysis does is it takes models that are basically observational HR diagrams, and you can fit them to real data to determine a star's type and its stellar properties. So for example, based on what a star best fits within the isochrone, you can see its luminosity, its surface temperature, and then tell what kind of star it is, which then tells you its approximate radius and mass, which are all very useful information for analyzing transiting planets. So using Dartmouth's isochrone models, our authors today got the stars data, and then were able to start eliminating down their list of candidates to narrow down which ones could be exomoon candidates. So first, in round one of preliminary eliminations, our authors simply fit the light curves of the transiting planets to planet-only models and planet-moon models to see which one they better fit. And any light curve that better fits planet-only models were immediately eliminated, as I just immediately told them right off the bat that the planets likely didn't have moons attached to them. Next, they looked at the orbits of the planets, and based on our understanding of planets and moon formations, planets with supereccentric orbits likely wouldn't have exomoons. So any planets with overly eccentric orbits that were circular were eliminated as well. Finally, our authors also eliminated any planets that didn't exhibit TTVs, which stands for time transit variations. And this is because if there was an exomoon orbiting the planet, we expect there to be, as the name suggests, variations in the transit time due to the tugging of the gravitational tugging of the moon on the planet itself. So any transit that didn't exhibit this property likely didn't have a moon orbiting around it, as that's an expected property. And after this first round of eliminations, our authors were left with around 11 candidates. So they conducted a second round of eliminations by adjusting models and again, verifying eccentricities and model fittings. And from there, they eliminated some more candidates and narrowed it down to 3 specific potential exomoons. And then they took a closer look at each of them, which we'll be getting into. So first, there's candidate 1, KIC 868112.5.01. Now, you can see the planet moon fitting down here, and immediately there's an issue that our authors noticed, and that's that the transit dips that occur within this light curve are inconsistent with what we expect out of exomoons, as exomoons would likely cause dips that are equal in duration, that are very consistent. And that doesn't fit with what we're seeing here. And our authors then determined that this is likely a dip actually caused by instrument error and or blending from background stars, really bright background stars. Which can cause also these variations in brightness that we're seeing here. And when they fit a new model of planets plus blending of background stars here, you can see that it fits much better than the planet moon model. So that just completely eliminated this candidate as having an exomoon. Next, let's look at candidate 2. So first there's Kepler-1780-bi. And there's a lot of fittings that you can see here, but essentially what the authors immediately noticed is that this planet is actually orbiting a star that's known to be very active and which also has several dark spots. And this means that it's very possible that this active star created a false positive for exomoons with its dark spots. And this is actually really similar false positive that occurs in exoplanet searching, where the dip in brightness caused by a star's dark spot can be mistaken for an exoplanet. And in this case, this is kind of paralleled in the exomoon searching process, as the planet passing in front of likely 2 dark spots caused the dip in brightness rather than an exomoon itself. Which is just a really interesting parallel. And you can see here in the model fittings that ultimately the planet only with 2 spots model fit better than even the planet moon model. So again, this was eliminated as a candidate. Finally, we have candidate 3, Kepler-1780-bi. And immediately you can see here that the light curve fits super well with the planet moon model, and that as previously discussed, there's the expected duration, which is very consistent between the 2 transits found. And this tells us that there's a good chance that this may be an exomoon orbiting this planet. Now, there's still the off chance of this being a false positive, as such variations in the transit could also be caused by another exoplanet tugging on our planet itself. However, our authors determined that the chances of this is less than 1%, which ultimately makes this a fairly good candidate for an exomoon, and something that, as there's not too much uncertainty about it or error, a potential error within it. So that gives us results of our survey today. To recap, 1 out of the 70 candidates were found to be an exomoon candidate. However, the authors really emphasized the need for more data and observations to confirm the existence of whether or not this is an exomoon. There's a history of people jumping too quickly to conclusions at these discoveries. So more data and observations are needed to confirm this. Assuming this moon does exist, however, it's very interesting in its properties, actually. So Kepler-1780bi, as determined by our authors, is, if it exists, 2.61 Earth radii with its radius. It has an orbital period of 4.6 days, meaning immediately you can see it's very big and very close in towards its planet. And we'll dive in a little deeper into this in the next slide. So comparing it to the moons of Jupiter and Saturn, for example, the biggest moon of Jupiter is Ganymede with an Earth mass of 0.431 Earth masses and an orbit of 7 days, while Titan, the biggest moon of Saturn, has 0.404 Earth masses and an orbit of 16 days. And both of these are terrestrial moons that are orbiting relatively further out than our candidate today. In fact, if you look at the mass of today's candidate, you can actually see that based on our understanding, this moon would actually be the size of a sub-Neptune, even bigger than the Earth, and ultimately an icy gas giant type of planet. Which is unlike anything that we see in our own solar system. It's much larger and orbiting much closer in, which is very interesting. What it is actually similar to, however, is another exomoon candidate discovered in 2016 by Tichy et al., which is known as Kepler-1780-bi. So both of these planets are sub-Neptune-sized exomoon candidates orbiting very close into their planets. And this is actually a very interesting trend with exomoon candidates, as it exposes, again, the bias with the transit method. Just like how it is with planets, the transit method likely would favor exomoons that are orbiting closer to their planets that are bigger, as bigger exomoons cause more noticeable changes in the transit depth. And a closer orbit means more often transit events, which are easier to detect for us. And in this way, these sub-Neptune exomoons seem to parallel the trend of hot Jupiters found by the transit method, which is just something to keep in mind, and just a very interesting trend to take note of moving forward into an age of new exomoon discoveries. Exomoons have great implications to our understanding of the dynamics of solar systems, how they form, and on habitability. For example, just look at our own moon. It stabilizes our orbit and plays a huge role in the habitability of our planet. So with all this in mind, it's very interesting to see how this will develop, this field of exomoon discoveries. So until next time, bye.